US Physics Olympiad, year 2019, USAPHO. Final round. Problem B1. Strain in the membrane. The wall of a neuron is made from an elastic membrane which resists compression in the same way as a spring. It has an effective spring constant K and an equilibrium thickness D0. Assume that the membrane has a very large area A and a negligible curvature. The neuron has ion pumps that can move ions across the membrane. In the resulting charged state, positive and negative ionic charges is arranged uniformly along the outer and inner surfaces of the membrane, respectively. The permittivity of the membrane is epsilon. Question A. Suppose that after some amount of work is done by the ion pumps, the charges on the outer and inner surfaces are Q and negative Q, respectively. What is the thickness D of the membrane? Question B. Derive an expression for the voltage difference V between the outer and the inner surfaces of the membrane in terms of Q and the other parameters given. Question C. Suppose that the ion pumps are first turned on in the uncharged state and the membrane is charged very slowly, quasi-statically. The pumps will only turn off when the voltage difference across the membrane becomes larger than a particular value V. How large must spring constant K be so that the ion pumps turn off before the membrane collapses? Question D. How much work is done by the ion pumps in each of the following situations? Express your answers in terms of K and D0. Case 1. K is infinitesimally larger than the value derived in part C. Case 2. K is infinitesimally smaller than the value derived in part C. Solution for problem B1. Question A. One charge layer by itself creates an electric field Q over 2 epsilon A in each direction. So the force between the two sides of the membrane equals this expression. This electric force is balanced by the spring force equal Kx, where x equal D0 minus D. So finally we have expression for D. That will be this expression. So that's the answer for question A. Solution for question B. The electric field inside the membrane as produced by both the left and the right plates is Q over epsilon A. So the voltage between them is this one. Now we can insert the expression for D from part A, and we have V equal this expression. From this equation we can see that as a charge is increased, first the voltage will increase, but later it will decrease again. So that was solution for question B. Solution for question C. The voltage V first increases and then decreases as a function of Q, which implies that there is a maximum voltage Vmax to which the membrane can be charged. This voltage can be found by taking the derivative from this V and equalizing to 0. So from this equation we can find that D0 equals this expression. So this equation gives us a charge corresponding to maximum voltage. And if we insert this charge to our expression for voltage, we have V maximum equal this expression. For the ion pumps to turn off, we must have Vmax greater than Vth. Otherwise, the pumps will continue to move charge across the membrane until it collapses. Setting Vmax greater than Vth and solving give us K must be greater than this expression. And that was solution for this question. Solution for question D. In the first case, when K is infinitesimally larger than the value derived in part C, then the threshold voltage Vth greater than V maximum, and the ion pumps turn off before the membrane thickness D reaches zero. The work W done by the ion pumps is equal to the potential energy of the system relative to the uncharged state with the Q equals 0 and D equals 0. That is simply potential energy for spring plus potential energy for charged capacitor, where capacitance equal this expression, X equal this expression, and D equal this expression. Now let's put all these expressions to our equation for energy, and we will get this value. K being infinitesimally larger than the critical value means that the ion pumps turns off just as the voltage maximum Vth is reached. At this point the charge Q approach QV maximum, which is this one, which we counted in previous questions. And finally we have total work done by ion pumps equal 5/18 d0 square. This happens because we inserted instead of Q this QV maximum. That's answer for part 1. In case 2, if K is smaller than the value in part C, then the threshold voltage is larger than the stopping voltage Vth, and the ion pumps continue to work until the membrane collapses to D equals 0. At this point there is no electrostatic energy in the membrane capacitance is infinite, and we have energy equal just 1/2 K d0 square, which is mechanical energy for fully compressed spring. That was a solution for question D, and that was a full solution for problem B1.